hopefully you had a good lunch and you won't sleep here. I'll make sure you don't. Okay, so in the it's good. Okay, so in the morning we focused on the exoplanet detection techniques. Okay, how we find exoplanets using different techniques like radial velocity, transiting, direct imaging, microlensing, and we went into the details of how the radial velocity technique works, and we calculated also like what will be the velocity amplitude for the Jupiter-like planet and Earth-like planet. Similarly, in the transiting technique also we did what will be the transit depth for a Jupiter-like planet and Earth-like planet. And from that we get a general idea, you got a general idea about how exoplanets are detected and how we constrain their different properties like mass, radius, orbital period and all those things. So now as we move forward, I'll just continue with this and slowly transition into exoplanet atmospheres, because that gives us the information about what's there in the planet, which gases are there, if there are any clouds, all those things. I'll first start with the motivation as well. Why we need to study the planet's atmosphere? Why is it so important? Okay, so we'll slowly proceed towards that. Okay, this is the exoplanet phase curve. I'll come back to this later again. So, and to give you an overview of the, we were learning about the exoplanet detection. So, where we are heading in the detection part. So, with the Kepler, we only looked at a very small part of our Milky Way, because it was just one part of the sky it was looking at, and that is with this area it was focusing on. So, all the more than like 5,000 exoplanets have been detected only in this part of our Milky Way, okay, using Kepler. But as we move in the further, we need to get a overall population of how the exoplanets are distributed in our Milky Way itself. Like are in a particular part, if you have this kind of exoplanet, in the other part, do you have different kinds of exoplanet? We don't know. So for that, you need to do a whole sky survey. Okay, and that is what we are going in the future towards. So, and this is like just to give a pictorial view of this is from Stellarium actually. This so this resembles something? What does this resemble? Can anyone guess? Yeah, detector actually, yeah. So it seems like a detector. So that is because Kepler was looking at one part of the sky, so it was only able to detect all the planets that come on that detector. So all the planets are within this detector. You will see that this is all the planets we have detected. And to give you a pictorial, if you go at the night sky, if you spot these three stars, they are called the summer triangle stars, the Altair, Vega and Deneb, that field of view lies in that area. So most of the planets that we know currently lie in this area. Okay, but this does not represent the whole Milky Way galaxy, the spread of the exoplanets that exist in our Milky Way galaxy. So for that, a mission was launched around 2020-21. It's called TESS, Transiting Exoplanet Survey Satellite. So this is doing a whole sky survey, unlike Kepler. So this is like choosing a one part of the sky, doing observations for some time, then changing the sectors. So this is a sector-wise doing, and in that process, it is covering the whole sky. Of course, like if you are doing a whole sky, then you don't get sufficient time on particular sector. But it's like give and take. Like for some things, it is very beneficial. Like the main aim of the TESS mission is to identify exoplanet candidates that are very close to the our solar system, or close to the Earth. So it spends some time on that sector, identifies exoplanet, then moves to the next sector, and that is how it does it sequentially. So it's Kepler is gone. TESS is currently in operation, and from this we are getting more and more planets. Each day, if you go and check, the number is increasing. We have reached 5,800, and it is really keep on increasing. And then in the few years, then we'll have the Plateau mission led by ESA that will again discover more exoplanets, and then and the ground-based surveys are still going on, like many WASP wide-angle survey for planets, and many other ground-based surveys around the world. They are also detecting planets, but they are slow because they cannot do like whole sky like TESS does. So, but that is going on. So, in terms of detection, we are heading towards finding more and more planets, and with lot of variety that we are heading towards, and this kind of surveys are helping us to do that. Okay, So we have detected an exoplanet. So what do we do next? Does that finish? It's done? No. So that is where the next part begins. Does it have an atmosphere? Are there any clouds or haze? What is the atmospheric composition? And finally, everyone likes to, are there any aliens? That everyone wants to know that, okay? So that is where we need to start understanding the details of like what's happening in the planet's atmosphere. And that is what I will go in the further section. So why is atmosphere important? What is the importance of atmosphere for life? So the best example is our own Earth. Now, if you think of Earth, the radius of the Earth is around 6,400 kilometers. Out of that, like most of the atmosphere lies within the 100 kilometers, most of it. It's a very thin part of it. But that thin part is what makes life exist on Earth. Because of that thin layer of atmosphere, because if atmosphere would not have been there, first of all, there wouldn't be anything to breathe, and the other is the temperature would have been very low. So it is that thin layer of the atmosphere that first gives us the gas that we breathe and we survive, each and every one of us, even the plants. And then it gives us that safety blanket of temperature on which the life can evolve. Okay, so this is what the atmosphere is, why it is so important for life. And then why atmosphere is important for habitability? Then we have an example in our own solar system itself. Like we have a twins, Earth and Venus are like twins because they have similar sizes. Okay, but why one is like full of life and one is like full of like hell structure, like means you have sulfuric acid rains, the temperature of 700 Kelvin on its surface. So such high temperature where like it's very, very difficult for life to evolve. Currently there are many theories that propose that there might have been life earlier in Venus, or it might be there in its atmosphere, but currently we don't have any proofs for that. So why one went in this way and one went the other way? So this is entirely because of the atmosphere. How did the atmosphere of these planets evolve over the years? Like Earth is like nitrogen dominated atmosphere, the temperature is such that the life can evolve. But Venus is such a carbon dioxide dominated atmosphere where sulfuric acid rains are there and very high pressure. So at the surface it's very, very difficult for life to evolve. The pressure is so high that anything you take, even metal structures will get crushed. It's the same pressure as you go like 100 kilometers beneath the surface of the ocean. So it's a very difficult environment for life to evolve. So this is where the differences in the atmosphere of Earth and that of the Venus is basically what took them to different paths. And that is why it is very, very important to understand what the atmosphere of exoplanets are also made up of. Because if you want to find life in any particular planet, we need to first understand what its atmosphere is made up of, what it contains, and that will help us in like calculating if the planet can be habitable or not, if there is any possibility. Okay. So, and then in doing that, we also have to understand that there are three different ways fundamentally by which a planet can get its atmosphere. Okay. So it can be any of these three ways. Okay. First is accretion from the nebular gas during the formation of the planet leads to formation of primary atmosphere, which most likely will be hydrogen and helium dominated. Okay. So when your stars and planets are forming from the nebula, initially there is abundance of hydrogen and helium. Okay, and that is what the planets will take over. So that the first atmosphere, which is called the primordial atmosphere, will be hydrogen and helium dominated. Okay, generally that is the case. So at some point of time during the formation of Earth also, Earth would have had hydrogen and helium dominated atmosphere. But slowly over the time, it gets stripped away because hydrogen and helium dominated atmosphere will be like very low mean molecular weight. So it slowly it will go out. So where does the next atmosphere comes from? So there, the outgassing from the planetary interior can lead to the formation of the secondary atmosphere, which is predominantly nitrogen, CO2, sulfur dioxide. It depends on what is there in your planet's interior. Okay. So if you have volcanoes, like an example, volcanoes spew off lot of gases. So these all gases will ultimately slowly build up your atmosphere. So I will come back later that how can we actually constrain even the planet's interior by measuring the atmospheric composition. Because what's there in the atmosphere, the secondary atmosphere, can tell you what's there in the planet's interior. Okay. So at some point of time, when Earth was losing its hydrogen and helium dominated atmosphere, some gases from the interior like carbon dioxide, sulfur dioxide, that would have been outgassed in the Earth's atmosphere, and it would have made the secondary atmosphere of the Earth. And currently the Earth's atmosphere is dominated by nitrogen, but it is not necessary that maybe 1 billion years ago or 60 million years ago it would have been the same. One of the current like understanding from the geologists suggests that Earth was much more warmer than it is currently before. Like maybe when dinosaurs were present, the atmosphere was completely different than what it is. In fact, it was much more suitable for life at that point of time. So so the evolution of atmosphere itself of a planet plays a very, very important role in how the life itself would have evolved on the planet. Okay, so that is one more reason for studying the planet's atmosphere. And the thing is, there's a lot of variety that we see in our solar system itself. Like if we see in the atmosphere in our solar system, we have Venus, CO2 dominated, some nitrogen. We have Earth, nitrogen dominated, only planet with oxygen, so that's clearly something different from other planets. Then we have Mars, again CO2 dominated but less pressure. Then we have the gas giants, which have almost similar structure. Jupiter, Saturn, Uranus and Neptune, hydrogen and helium dominated. But like Uranus and Neptune, because they are colder, they have some amount of methane also in them. And then we have Titan, which is like a moon, which is an outlier, which has a dense atmosphere. It is the only moon in our solar system that has such a dense atmosphere, a nitrogen dominated atmosphere. Titan, I guess most of sorry? Of? It's a nitrogen dominated, yeah. So we have actually measurements from one of the probe was actually sent, the Huygens probe. It actually landed on Titan, and while coming down, it took the atmospheric measurement, and even they found lakes of ethane and methane on that, because it's so cold that your organic gases will also condense. Okay, so these are all, so the main aim for me to show you this plot is that there is such a large variety of atmospheres in our solar system itself. So now you can think that the exoplanets that we are finding, there is so much variety in exoplanets, so, and more possibilities are there for the atmospheres that they could have, because these planets are around different kinds of stars at different distances from their host stars. So all these will lead to different composition. A lot of variety can happen. Okay, so that is the reason that this becomes very exciting. Like when we study exoplanet atmosphere, we cannot predict like what it will be there. We try to do that using our models, but it's when we come get the observations and we interpret them using our models, we find many new things that we don't even expect. So a large variety of this is a large variety of planets and their atmospheres are possible. Okay, that should be the main takeaway point from this. Okay, so earlier I was telling about detection of exoplanets. Now detecting exoplanets itself was challenging. Okay, now studying their atmosphere, which is just a small part of it, that is much more challenging. Okay, so exoplanets are very far away, so can we really study their atmosphere? So so the first study of exoplanet atmosphere was done in 2002. This was the first paper that detected an atmosphere for the first time in exoplanet atmosphere. Okay, and in this case, they detected basically a sodium feature in HD 209458b, and a hot Jupiter exoplanet. And from that, like we got a confirmation, yes, we can study exoplanet atmosphere and constrain what's their composition. This was somewhere around 2002. And still, then people started thinking, yes, so now we have detected sodium. Now, could there be any other gases? Now we have detected gases in hot Jupiter planet. Can we do that for different warm Neptune-like planet, or even Earth-like planets? Is that possible? So that, then people started thinking, we started utilizing resources, our telescopes, to study different classes of exoplanets and finding what are the different gases present in them. So I'll go through the details of how do we. This was done, by the way, using Hubble Space Telescope. So this is using the Hubble Space Telescope. This instrument, this measurement was done. Okay. So what are the big questions that currently drive the field in exoplanet atmosphere? So what is the diversity in exoplanet atmosphere? Like I was telling you, like we don't know what kind of different atmosphere exists out there. So that is the main question. What is the diversity out there? How do exoplanets and their atmospheres form and evolve? Where does it come from? How does it evolve? Is our solar system and Earth unique? Like we have life only on Earth. Is that unique or is it common across the Milky Way or in the universe? How did we get here? How did we get to an atmosphere that is nitrogen dominated and oxygen is there, and so that life is able to survive? Like, this is the question of our survivability. We currently don't even know that where we came from. So we are trying to answer that. And ultimately, are we alone in this universe? Like, are there any other species that are present on other planets? It may be the alien form or the or simple bacteria or plants or trees. We don't know that. So all these are the big questions that are currently driving the field. And within that big questions, there are like these detailed questions that we currently try to answer. Which molecular species are present in exoplanet atmosphere? What are their abundances? Abundances means how much is the amount of them? What is the temperature distribution? What kind of chemistry? What thermochemical processes are dominating? Do these planets have thermal inversions? I'll talk about that later. Are there, in the morning someone asked me about like, is there a catalog? So this is regarding that. Like, people are trying to do that cataloging. Can we have classification like stars? Then these are other details, metallicity and carbon to oxygen ratio. I won't go into detail. Are they cloudy or hazy? Like, we see clouds very common on Earth. So are there clouds or hazes in them also? So these are the detailed questions we are currently trying to answer. So how do we answer this question? So the method is the same, the transit method. The fundamental method is the same I was talking about in the morning. The planet goes in front of the star, there's a dip in the brightness, and that is how you find the planet. Okay. Now if I want to study the planet's atmosphere, then what do I do? Any guesses? Spectroscopy, yeah, good. Yes, so how do I do that? Means, what is the difference between that and that what you're talking about, the spectrum?
Planets are like line emission spectrum. Because of the atmosphere. Different colors, their amount will say like consumption. Line absorption. Yeah.
So we are, so this, what, this spectrum that you're talking about, so where is this, the radiation coming from?
The host. We take the sun itself and then we take Bell transmitting and we can subtract and find out how is it.
Yeah, yeah, so we are all on the right track. So I will talk about that, the transmission spectroscopy that we call it. Same, like I have in, so essentially what do we do that is, we do this in multiple wavelengths. When you want to detect a planet, you take a broad band, like you take 0.5 micron to 1 broadband signal, you integrate over all the wavelengths. But when we want to do atmospheric studies, you use a spectrograph and divide that into multiple wavelengths, because ultimately we want to get the features of different gases. So I'll come to that in a minute, okay? But before that, if you want to do atmospheric study, we can't go and study all 6,000 of those exoplanets. There's so many of them, we don't have sufficient time. So how do we choose which planets are the best for atmospheric studies? Okay, so the one thumb rule here is, larger the atmosphere, the better it is for atmospheric studies. So because the larger is the atmosphere, because the atmosphere is large, it will lead to a bigger change in your signal, and that is how we will be able to detect. So how do you compute or calculate how big is the planet's atmosphere? Because we don't have any measurements yet. So how do we do that? Larger the mass. So in fact, it will shrink the atmosphere, isn't it?
But it will retain more, like more elements which were being drawn away from the solar wind at the time of formation.
Okay.
Maybe how come the U craft.
No, it means you are on the right track, but one more, 2 or 3 more factors come into picture there.
Find the planets which are probably in the habitable zone of the stars and go there.
No, but why would that lead to a bigger atmosphere?
The size of the planet.
Size of the planet means, but the size of the planet also includes the atmosphere, isn't it? We don't know how much of it is atmosphere and how much of it is actually the.
So during the transition, we'll get a U curve, right?
Hmm.
If that is like more curvy, then we could say that this atmosphere is causing this more curvy.
In a sense, if the transit depth is higher, of course, yes, we can say that it is good for atmosphere. So there is a theoretical calculation that we rely on to get this, and this is called atmospheric scale height. So that is what I will go into. So here, so the scale height, the definition of scale height is height at which pressure decreases by a factor of E. Okay. So if you consider Earth's atmosphere, if you start from the surface, the height at which the pressure decreases by the factor of E is called the scale height of the Earth's atmosphere. And this calculation ultimately comes to H is equal to kT by mu g. So you were talking about the G, no? So that factor also comes into the picture. But here two more governing factors are temperature of the planet and mu, the mean molecular weight. The mean molecular weight actually plays a very, very important role. K is a constant, it's a Boltzmann constant. So if the planet's temperature is high and its mean molecular weight is low and gravity is low, then it will have a higher scale height compared to the other cases. So in that case, your planet will become, the planet's atmospheric scale height will be higher, and then you can say, yes, this is a good target for atmospheric studies. So using this atmospheric scale height measurements, we decide if a particular planet is good for atmospheric studies or not. That is one criteria. Then the second, one more criteria which I don't talk about is because we also have to consider if the signal that you are getting is sufficient enough. So the magnitude of the star matters, because ultimately we are collecting the photons coming from the star. So if the star is like either very far away and or it's very dim, then we won't get the sufficient number of photons. So magnitude of the star also matters. Okay, this matters for the atmospheric part, but the magnitude of the star matters like for the signal strength. So these are the two factors that we generally consider while selecting targets for atmospheric studies. Yeah.
How do you calculate mean molecular weight of a particular planet?
Very good question. So this is like a chicken and egg problem. Okay. So I haven't yet measured the atmosphere. I'm telling that I need to use the mean molecular weight. So good question. I was expecting this. So the thing is, this is the big challenge. So here we have to rely on our theoretical understanding of planets and their atmosphere. Like if a planet is a hot Jupiter or a warm Neptune exoplanet, then most likely it will be hydrogen and helium dominated. So if you take a hydrogen and helium dominated atmosphere, then from that you take hydrogen molecular weight, helium molecular weight, you combine that and you get the mean molecular weight of that, and then you use that. But you are right, like if you are going for planets like super Earths or different, where we don't know anything about the atmosphere, then it becomes a really challenge. Then you have to, it's like then you have to try all the different possibilities. Okay, and then it becomes a very difficult to convince people to give you time. Yeah?
We also need the planet's gravity. Now,
Huh.
Assuming we find the existence of the planet using the transit method,
Huh.
we discussed in the morning that we cannot find the mass.
Correct.
How do you again compute that?
Radial velocity. So all the
You need to have.
yes, so that's a good point you have raised. So all the planets, if we want to do their atmospheric characterization, if we want to study their atmosphere, we need to have its mass and size both known. So means only the planets that have been studied using radial velocity and transit techniques are mostly used for atmospheric studies. Otherwise, they are not done, because otherwise your constraints will be like very weak. So that is where from radial velocity you will get reach. Okay. So this is a rough calculation that I'm showing you. What is the scale height of the Earth's atmosphere? Okay. So if you take Earth's mean molecular weight, 78% nitrogen, 21% oxygen, 1% argon, 28, 32, 40, you know the molecular weight. So from that, if you calculate the mean molecular weight of the Earth's atmosphere, it comes to 28.96. The temperature is around 15 degrees Celsius, 288 Kelvin, G is 9.8. So if you put all that, you plug in H, kT by mu g, the scale height of the Earth's atmosphere comes around 8.4 kilometers. Okay. So this is calculation, so you should write this down because there's the next is the quiz. So now the scale height, yeah, go ahead. Yeah.
G also varies, but at this small height.
Yeah, because this is a rough calculation. Yeah, definitely the G
But
varies.
the height is also very small. So
Yeah, it won't vary that much. So now here I am showing you the calculation for the scale height of the Earth's atmosphere. Now suppose you want to calculate the scale height of a hot Jupiter atmosphere with following properties. Can you do that and tell me what value you get?
sir, and that formula, is it valid for thin atmosphere as well as thick atmosphere?
Yeah, I mean generally this is a rough calculation, so you can use for means both of them. Because ultimately you want to get how much is the, it won't be applicable for atmosphere like that of Moon or Mercury. There is no atmosphere at all, it's very thin. For that we cannot use them. But like Earth, Venus, Titan and all that. So K is given to you, G is there, T also you have. Only thing you have to calculate is the mu. And here also I'm telling you it's hydrogen and helium. So 85% hydrogen, 15% helium. How much you're getting? Yeah, I need just rough order of, you don't need to like point this and this. Order of, how much?
573 kilometers. And 5.7, 10 to the earth.
Yeah, you will get somewhere around 600 kilometers.
Yeah.
Correct. So now the take, most of you should get it, it's a simple calculation. But see the order of magnitude. For Earth, how much we were getting? 8.4 kilometer, 8 kilometer. And for a hot Jupiter planet, we are getting 600 kilometers. So almost 100 times larger. This is what I was telling about. Like based on the scale height, I can tell if the planet's atmosphere is big or not. So for Earth's atmosphere, if you want to detect currently with current telescopes, if you want, even with James Webb Space Telescope, studying Earth like atmosphere is like almost impossible. It's very, very challenging. But hot Jupiter atmosphere, because of its large size, the large scale height, we are able to characterize them. And that is why over the first exoplanet atmosphere was detected around a hot Jupiter. And since then, because we are finding exoplanets and we are studying, we are still refining our techniques. So we can only refine our techniques when we are able to detect something. If directly started studying Earth-like planets, we will not get anything. We'll just get flat lines, isn't it? So that is why the main focus over the last 15 to 20 years while studying exoplanet atmospheres have been the planets like hot Jupiter, warm Neptune, mini Neptune, where we can actually measure something, some signals. And the other reason is also that we need to get the diversity that exists out there. What are these different diversities that are present? What is the atmosphere of hot Jupiter like? What is an atmosphere of warm Neptune like? Does it vary in different parts of the Milky Way? What heavy elements they have? Is the atmosphere different around different kinds of stars? All these things we have to answer. So one of these criteria is the scale height to do that, and like you have done the calculation of yourself, and from that we can understand that hot Jupiter and warm Neptunes would be the best target for atmospheric studies. Yes.
Like, is this data real or is it just made up? Because Earth's surface gravity is 9.8,
Huh.
and we know that the escape velocity, like Earth can't hold up hydrogen. So this planet's surface gravity is 9.4, and you are saying it is composed of 85% hydrogen. So is it a
Yes.
made up data?
No. It is actually data. If you think a real exoplanet like HD209 also, it's like very close to that of that. So it can. So here you'll have to also think of the density of the planet also matters a lot, because these planets are massive. So that's why they are hot Jupiters. They are called. So their mass might not that be very high. No, but in this case, okay, let me see the 9.41, which I have taken. For this case, I have made up the data. So I'm just thinking for the case of HD209, how much it comes around. Let me look at the values in for HD209, and then I should be able to answer your question. But in many places, in many of these hot Jupiter planets, they won't be very massive, but it won't be as low as that of the okay. So it can be high, but they are also high temperature. So they are like very puffy planets, we call them, hot Jupiter. Okay, so the identifying suitable targets. Okay, so hot Jupiters and warm Neptune, that is why have been one of main targets for atmospheric studies, and that is why and they are also very close to their host stars. Okay, so it's a win-win situation, because if they are very close to their host stars, you can get many transits. Okay, so we can do, if you get more transits, then you can actually do the spectroscopic studies also more frequently. Okay, and plus their atmospheric scale height is high. So here is a pictorial that shows you that, like, many of the hot Jupiters are so close to their host stars that than Mercury is to Sun. They're very, very packed in, like 3-4 day orbital period, 10-day orbital period. So we also jokingly say that if someone lives on this planet, then every 10 days you can celebrate your birthday, because it will orbit every 10 days. And one more benefit of these are they are tidally locked. Anyone knows tidal locking? Yeah, so like the example there is of the moon. How moon is tidally locked to the Earth. So basically we only see one side of the moon, isn't it? Similarly, because they are so packed in this system, they are also tidally locked. Okay, the hot Jupiters are mainly tidally locked. So always the one side of, you have a constant day side and a constant night side. So this is a very interesting phenomenon, because for Earth that's not the case. But for this hot Jupiter kind of planets, or planets that are very close to their host star, they are tidally locked. Okay, so this has also implications for habitability if the planet is cooler. Okay, so once we identify, yes.
Since they're tidally locked, but they have such large atmospheres, can we expect to have convections in the atmosphere which will uniformly heat the entire planet up?
So that's a good point. So convection plays a role, but thing is, because they're so highly irradiated, the top part of the atmosphere is driven by radiation. It's only in the lower part of the atmosphere, you go deep down there, convection becomes very important. So I'll talk about that briefly. Like in different parts of the planet's atmosphere, different processes dominate. In the top it will be radiation, and in the bottom it will be convection. And that also gives me like the question that you are asking about that the G. The thing is that because of this, the planet is puffy, their radius is very high, isn't it? So the G is Gm by R square. So your radius is high. So even if your mass is low, it will compensate for that G value. You understand that? So that is where it matters. These are very puffy. So even if you have low mass, the planet itself is so big. Okay. So G will become lower value, even if the planet is massive. Okay. Yes.
Then there is a very high probability that the atmosphere, which is dominated by hydrogen and helium, should have been like it should have escaped the atmosphere due to the stellar events. But why didn't that happen?
No, so you are right. Actually, that is happening. So in many of these planets, actually we see that process happening. So we currently don't know what's the age of these kind of planets. For many of them, we don't know the age. For some, we might be knowing. But in many of these, we are observing that actually the atmosphere is slowly escaping. Like one recent detection that was happened 5-6 years ago, where we are clearly able to see the helium going away from, escaping helium from the exoplanet's atmosphere. So these all processes are also happening. Okay.
And what are the time scales over which these gases escape the atmosphere?
So, but it won't escape fully. Like you are expecting, like we lost the Earth's atmosphere. But for these planets, we have to understand that these are totally made up of hydrogen and helium. They don't have, we don't know, at least for now, we don't know whether they have a solid core or something like that. So it will take like quite a long time. We don't have current any understanding of like will it be able, will it completely lose or will it maintain that? That's still a question mark on the understanding in that area. Okay. So once we have identified, so I'm now telling you the procedure, like how do we actually do research in this case. So once you have identified the target, that is important for atmospheric studies, what do? You apply for telescope time. So have any of you like thought about like what does that mean to apply for telescope time? Have you applied for telescope time in your for your project or something? So generally what happens is like the observatories around the world, like they open up, they call for proposals. Even like you can apply even for time on James Webb Space Telescope and Hubble if you have a good science idea. Of course, you have to do work, do the simulations and everything. You have to convince the committee that your science is very important and please give me time, I will do a good science. If you do that, you will get time. Many of huh?
It's also very competitive.
It's very competitive. So the success rate for the JWST is like 15%. Out of every 100 proposals, only 15 pass through. Okay, and for some of them we don't have access sitting in India, like the VLT and all that, because they are European based. You have to like subscribe to that. India currently does not have subscription, but Hubble and JWST, they are open. You can apply for that and get time to do your science. And of course we have facilities in India which we can use, like we have the Devasthal Optical Telescope 3.6 meter, Hanley telescope, then in Mount Abu. Many of them, depending on which institution are you are. This is in Chile, VLT, very large telescope. Okay, so so you have identified your atmosphere, you apply for telescope time, and then you need to do your full reduction. Okay, so in the reduction, what we do for exoplanet atmosphere is, this is what the raw data generally looks like, the atmospheric study. So what we are actually measuring, we are measuring the planet going in front of the star and the dip in the brightness, and we are measuring this dip in different wavelengths, and this is what that spectrum looks like. And this involves a whole processing like dark, bias, flat correction, spectral extraction, wavelength calibration, white light curve extraction, and finally you get something like this as a spectrum. Okay, so I won't go into the details of this data reduction pipeline. So essentially this is what the transmission spectroscopy does. So earlier when we were trying to find the exoplanets, we were only measuring the light in a big band pass. Now we are doing this multiple wavelengths, and because of this multiple wavelengths, the dip will be different in different wavelengths depending on what's present in the planet's atmosphere. For example, if oxygen is present in the planet's atmosphere, the oxygen will absorb a particular specific wavelength, like 760 nanometers is one of the lines of oxygen. So if it absorbs, the planet will look bigger, so the dip will be bigger. Okay, if nothing absorbs, it will just pass through. So we won't, there is nothing in there. That is the result that we'll get. So measuring this in different wavelengths gives us the information about what's present in the planet's atmosphere. More than that, it also gives us at what amount it is present and also its temperature. Now this is very important. I'll talk to that in a minute. How you get actually pressure, temperature, the abundance of it, even clouds and everything. All this information you can get from this spectrum. Okay. And essentially we are using the simple concept, like the planet is going in front of the star, we are measuring that using a spectrograph, and different absorption lines are present, and we know that from our laboratory studies, like where different gases will absorb, and from that we get what we call as the transmission spectrum of the planet, and this is what the transmission spectroscopy is about. Okay. So this is actually a real transmission spectrum of one of the hot Jupiter exoplanet I was talking about. This is using Hubble Space Telescope for HD 209458b. So this planet is 159 light years away from us. So we are measuring an atmosphere of a planet that is 159 light years away from us. It's a sun-like star, 3.5-day orbit and 1200 Kelvin temperature. So what you see in this plot is a wavelength on the x-axis, and here we what is our transit depth? In the morning, RP is square by R star squared. So this is just a square root of that. Okay. So both are the quantities are used. You can use transit depth, which is actually the what we get from light curves, but you can use also the square root of that. Either of them is used while plotting. Yeah.
So the absorption spectra of different elements, they have to be known beforehand. But what if there is an unknown element? Then in that case,
Yeah, I mean that is very rare. Means, first of all, we are even struggling to find what is already there. can't even think about.
You can get novel.
And here, more than elements, you should start thinking of molecules. Because now we are in a regime where we are not looking at stars, we are looking at planets. So now the temperatures are lower, so your molecules start forming. And that is what we will look at actually. Okay, so in this diagram, you see all these observation points. You know? These are the points and these are error points. Now, what does this mean? Like I have shown you just the plot, the wavelength. This is what the observations we get from Hubble. We have processed it. We got a transmission spectrum. Like, what does that mean now?
So some part of the band is observed, some
Yeah, so basically the thing that you're saying is that in different wavelengths, the radius is different. So something is happening. Now, how do you get this? What is there in the planet? So there is where we require models. And that is where the planetary atmosphere models come into picture. And that is what I will go into the details. So this requires a very detailed modeling. Okay. So atmospheric modeling of exoplanets. So what it means like a model? So basically you have to simulate the whole atmosphere of a planet. So this is an example of that. Like it includes, so if you go out and look at Earth's atmosphere, what it has clouds, it has rain, it has radiation traveling, it has gases coming from everywhere like pollution, volcanoes, everything, plants emitting, everything is present there. We have oceans as well. So all these things are like basically contributing to a planet's atmosphere. We have radiation interacting with all these different constituents. So in our models, what ideally we need is we need to include all these components and then solve it using supercomputers, okay, and then compare that with the spectra. You generate a simulated spectra, compare that simulated spectra with actual spectra, and then constrain what's there in the planet's atmosphere, what's its temperature, what if there are any clouds or hazes, what's the abundance of different gases. So this models requires, like, you need to include chemistry, you need to include radiative transfer, opacities, clouds, dynamics, everything. All the different components have to be included. So this is very similar to when we learn about climate and weather models. Have you any of you coming from, like, done any work related to weather or climate for the Earth's atmosphere? So if you look at every day, you open your mobile phone and look at the weather prediction. So some or the other group in the world is running this massive complicated model that include dynamics, everything is like constantly being calculated, and that information you are sent across the world. That gives you a prediction. Yeah, that changes because weather and this is a very, very complicated system, isn't it? So it's modeling itself is a big achievement that we are able to do that. And this, now we have to do this for exoplanets. Imagine we don't have much information. So that is where the models come into picture. We have to give what might be the possible like spectra of that exoplanets, and that spectra we compare with our observations. Okay. So, so first, what's there in the atmosphere? Now for Earth, I can go and take a measurement and get what's there in the atmosphere. But now I have a spectrum of a planet and I don't know what's in there. So how do I start? So remember, if you are studying hot Jupiters and warm Neptune exoplanets, I can make a one good assumption, which is something called equilibrium chemistry. So what's there in the atmosphere for hot planets? We can do a calculation which is called equilibrium chemical calculation, which is essentially, you might have learned about Gibbs energy minimization also. So essentially the point here is, if I have a box and I keep some elements in it like oxygen, nitrogen, carbon in some amounts at a particular temperature and pressure, after a certain time, which all species they will form. How they will form H2O, they will form CO2, carbon monoxide, how much and which they will form. That is what we call as equilibrium chemistry, like abundances of species. A good example of this is like if I take like a M dwarf star or a brown dwarf or a hot Jupiter, because the temperatures are higher, the equilibrium chemistry will favor the formation of carbon monoxide. But if I go to the colder regime like Jupiter, it will favor a formation of methane. So it gives you a first order of estimate of what might be the possible species that might be present in the planet's atmosphere. So this is, it can be carbon monoxide in this case, it can be methane in this case. So that is where we do our first order of estimate calculation. What we do in our model is we include all these different elements, and depending on the pressure and temperature at different levels, we compute what are the different molecular species that might be present. Is H2O, CO2, CO, ammonia, and so on, many different things. And this is done using this calculation of Gibbs energy minimization. So this, yeah.
So in the previous slide, does A represent the albedo?
In this, oh, this in this case, yes. So this is more of a equation is just for representative purpose, but you are right. This is albedo here. Yeah. So what's there in the atmosphere we get from equilibrium chemistry calculation, and you will be surprised that this actually this calculation is what gives you the products that comes in the rocket engines as well as in your car engine, because they are also, you come across temperatures of 1000 or 1500 Kelvin. So actually, while doing this calculation, we use the experiments that were done in the 50s by NASA for testing their rocket engine. So the output of that actually we are using for these models. So it is very interesting how one thing helps other. Like that was done a long ago. Okay. Then the other important thing, like I was telling, like I need to know where these different molecules are absorbing. So how do we know that? Well, in the model, I need to include some database or some calculation which will tell us where these different molecules that are present in the, because in the spectrum you are seeing these different lines. But when I want to compare my models to the actual observed spectrum, I need to include them in the model. So this is where a lot of effort we put is basically include opacities or line absorption cross section for different molecules in our model. This will include water, sodium, potassium, all of these molecules we have to include in the model. And this and many of you coming from physics background will understand, like we have to include, like because they are present in the atmosphere, they will have pressure broadening, natural broadening, all these calculations we have to do. And we store them in our model. This is basically the backbone of our, becomes a backbone of our model. So here I am going to the bit of detail, so it is alright if you don't understand, and you can ask me later about the detail. I am going to the depth of how these models are made. And for this, this line list, I have written here two words, exomolar height, and these are the databases that we use for this calculation. So these people do experiments in their labs and tabulate, like at this particular wavelength, this gas is absorbing. So this tabulated data set we use. Or, yeah? Oh, opacities. Essentially, opacities mean how much a particular gas will absorb at a particular wavelength. So, means at which wavelength they will absorb and how much they will absorb. So that calculation is called as opacities, because that is ultimately we want to measure, isn't it? Like when we are measuring the transmission spectrum, the gas in the plant's atmosphere is absorbing something. So we need to include that in the model. Otherwise, we won't be able to compare the model to observation. So that is one important thing we do. Okay. So, so I was telling you earlier, isn't it, that I can measure the planet's temperature and pressure by measuring the transmission spectra. So this is where it comes into picture, because the opacities themselves, so different molecules will absorb differently at different pressures and temperature. And this is an example you see here for water. Now ultimately, if you want to measure water in different planets, we need to include them in all different temperatures. So here we have water at 500 Kelvin and 1500 Kelvin. You see the absorption cross section of water is very different at these two different temperatures. So if we are detecting like in the transmission spectrum, you use a model that includes water at 1500 Kelvin, it will have a different signature than at 500 Kelvin. So using this, we can actually constrain the temperature pressure structure of the planet's atmosphere. So so I will talk about that again. What does pressure temperature structure mean? So like outside in the Earth's atmosphere, now you see rain happening. So why is this rain happening? Because there is somewhere convection happening. The clouds are being formed, this is being rain. So this is ultimately the variation in the pressure temperature structure that is causing this. Like if the pressure temperature structure is such that the clouds can form, the clouds will form and it will rain. So on every day you might not be knowing that Bangalore airport, they launch more than the instrument called radio sonde that actually measures the vertical temperature structure of the atmosphere in Bangalore area, evening and morning, and that's the most accurate pressure temperature structure that you can. All the flights, everything rely on that. So But for exoplanets, I can't go and launch there. They are like, it will take me 70,000 years to go. So what do I do? So to get that pressure temperature structure accurately, I need to use my models. I rely on my models for comparing with the observation. And that's why those pressure temperature structure measuring that becomes very important. Okay?
So sir, the graph in red color is the observed spectra and blue color is the simulated score.
No, both are the, so these are, I'm just showing you the cross sections. So here none of them is a transmission spectra. These are the cross sections, means that if I go in a lab, take a water vapor in a chamber, shine light at different wavelengths, okay, they will absorb, but they will absorb differently at 500 Kelvin and 1500 Kelvin. So from this I'm trying to say that because there is a difference between 500 Kelvin and 1500 Kelvin, in my actual spectra I can differentiate if the planet is at 500 Kelvin or 1500 Kelvin using this. So because the temperature structure represents this, if you see. So the earlier someone was asking about convection and this, no, you can see the convection dominates here, radiative dominates here. Again I'm coming to this plot, I won't confuse it now. So the temperature structure governs which gases will dominate in different parts of the atmosphere as well. Okay. So now I understand that now I'm connecting many different things, so it might become confusing. So feel free to ask, because there are many things we are touching. In the morning it was more simple. Now because we are delving into a lot of physics, chemistry, everything we are combining. Okay. So ultimately the spectra is governed by the pressure temperature structure, and that also gives you the chemical composition. Okay. And that I was telling you the example of the Earth's atmosphere. Now, this is the pressure temperature structure of the Earth's atmosphere. So this structure is very, very fundamental for any planet's atmosphere and even for its habitability. That is why it is important to measure it. And that is why I was trying to say that, like, using this understanding that different gases have different cross sections at different temperature, we can use this understanding to measure the temperature structure of that exoplanet which are so far away. Because this is where this temperature structure will govern if there will be rainfall, there will be formation of clouds, will the temperature be enough for life to evolve, will there be a thermal inversion that will lead to formation of a stratosphere. All these things are governed by the pressure temperature structure. So it becomes very, very important for us to measure that. So here, do you recognize this? Have you seen this before, this plot? So this is where we live, most of us, the troposphere. This is where the aeroplanes fly, the stratosphere. And this is, most of the atmosphere is contained within it. But this structure is what makes life possible on Earth. Like, there is an ozone layer that prevents all the UV rays from coming down. Here we have a temperature that is favorable for life at the ground. So this pressure temperature, constraining this becomes very important for exoplanet atmospheres as well. Okay. So now this is too detailed, I won't go into. So this is, I'm showing our model in a nutshell. So what do you do is, we need to solve our radiative transfer equations with chemistry, compute opacities, and this is done iteratively until we get a pressure temperature structure that is in hydrostatic equilibrium and it conserves the energy. So ultimately what we are doing is, we are getting a first order estimate of the planet's pressure and temperature structure without any observation, theoretically. So you have a radiation coming from the star, it will interact with every gas, it will in the atmosphere. We need to calculate that. Then that will depend on what's present in the atmosphere, but that will also evolve, because temperature will change the chemistry, then chemistry again changes the temperature. So there's the feedback happening. That's why there's a feedback loop going on. So ultimately we want a pressure temperature structure that's in radiative convective equilibrium. So I think that might be too much for this class, but of course if anyone wants to discuss, please let me know. So the main aim is to get a first order theoretical estimate of a pressure temperature structure, and using our models we do that. Okay. And we also need to include atmospheric scattering. Okay. When the radiation is going through the planet's atmosphere, it will be absorbed by the gases. We have included that, I told you. But also it will be scattered. So this is how, like, why we see the blue color of the sky or the sunset is red. This is because of the scattering. So do you know about Rayleigh scattering? So this is the Rayleigh scattering process that is in it. So these all processes also we need to include in our models. And that, because ultimately what we are doing, we are trying to replicate how the radiation is interacting with the atmosphere. because we want to compare with absorption. So we need to include all the processes that are happening in the planet's atmosphere, and scattering is one of them. Okay. And finally, we get something called a model transmission spectra. Don't worry about the equation. So ultimately, what using the model, see, remember in the observations, what we were getting is the transit depth, how the planet's radius varies in different wavelengths. Now using the model, we exactly calculate the same thing, because we need to compare our models with observations. Okay, so we have included everything in this model, and all the information about the scattering, absorption goes in that tau term. Okay, so if anyone is like really interested, they can go through the details of the derivation of this in our papers. This all is there. So from this we get the model transmission spectrum, and finally we get this. Now you see, earlier I was showing you, just one second, I'll take the, earlier I was showing you the observations. Now I have included the model, and now you see what all we have detected in the planets. Okay, yes.
What does TOA stand for?
Oh, top of the atmosphere. TOA stand, it was there earlier, is it?
Yeah,
Yeah, top of the atmosphere. We are integrating from the opaque part of the atmosphere to the top of the atmosphere. Okay. So essentially, now you see, earlier we were seeing the observation. So this is the wavelength, this is RP by R star, this is square root of transit depth. Now you, so in this, what I have done is, so this is from one of my papers only. So where I had generated a large grid of models, more than like 100, like 10,000 models with different parameters. And all those I have fitted to the observations to find out which model explains the observations the best. And this is that model I'm showing you, which best explains the observation. And here what you see, so in this Hg245, we have detected sodium. Okay, so we have a sodium detection in that atmosphere. This is not like I have discovered, this was the first detection, remember, 2002, first detection of an exoplanet atmosphere, this is the same. But in that, potassium was not there, which came later with more observation. We have potassium, we have water. So water vapor, this is but in vapor form. So we have water vapor, sodium, potassium, and this is that Rayleigh scattering slope I was talking about now. So that's why when we include scattering, we can detect that Rayleigh scattering slope also. This is the reason why the sky is blue. We say, no, the Rayleigh scattering, this is that. So we have detected now the same processes that are happening on Earth are also happening on other of these exoplanets, and we are able to detect them. Okay, so this is the main takeaway point, like using the models we can constrain. Yeah?
Deadline is an average spectral view, or is it?
Which one?
The line you just put?
Yeah, yeah.
That's an average spectral view.
So it's a model spectrum. So when you say average, what do you mean?
Okay, average means out of many.
No, it's a best fit model. Best fit. So out of like 10,000 models, one of them like best explains the observation. So that is this best fit model. Yeah. So this is that best fit model that is explaining my observation. So this is where we are combining. I was saying we are getting observations which are in this blue color, and then we apply our models which include all these opacities, chemistry, everything is combined, and we then interpret our observations, and from that we can constrain what's there in the planet's atmosphere. Now here I am showing you just like sodium, potassium, water we have detected. But in my model, I also have information that how much amount of that is there. Because only a certain amount of water will produce that feature. If the water is less, it won't match the spectral feature. So I can constrain how much amount of that is there. Then also have information of what pressure and temperature structure is matching this. So that all information I'm not showing here, but I have that information. So from that, then we can constrain what the plant's atmosphere will be like. What's the temperature there like. All this information we can constrain. Okay. So now just this is one of the quiz. So suppose using the template, okay, like this is the transmission spectrum on your left side, wavelength and RP bands. This is the overall transmission spectrum of the planet. Now on the right hand side, I have shown you different gases. This is the absorptions cross section of different gases. So in this, I want to give you a overview of how transmission spectroscopy works, how we determine what is there in the planet's atmosphere. So can you just look at this both and tell me this is a spectrum I've created from my model. Can you tell what's there in the planet's atmosphere? Which all gases are present? Methane. How is that you're saying? one may be
Sodium and potassium.
sodium and potassium. Good, yeah. So these lines you can see, they are matching. Sodium and potassium are matching. Then anything else? Lithium is there. Anything else? CO2 is it there? May not be. There's a lot of water in here. A lot of water in here. You see. But from looking at the eyes, it will be difficult. Okay. So the point I wanted to convey that is like you are doing with this, we don't do with eyes. Like we don't look at it. So in our models, so the transmission spectra that we get from any planet is a combination of all the different molecules that might be present. Because ultimately what we are measuring, how much light is blocked. Now at a given wavelength, there might be a combination of two molecules that might absorb. That then becomes very tricky. Like here, if you see, like in this regime, there is water absorbing, there is some other molecules that are absorbed. So in that case, what do we do? So it becomes very tricky because all of this is combined in this transmission spectra. So we have to decouple these effects. And there lies the challenge. Like we need to have broad wavelength coverage, like more, in your models you need to include more gaseous species. All these things have to be taken care of when we want to interpret our transmission spectral observation. So it's not that simple as like just one or two molecules you can use, because we don't know what will be there in the planet. It's a combination of all of these species that comes into picture in this. Okay. And here I want to also clarify things like there are two ways. So this picture nicely represents like how we actually interpret the observation. So there are two ways to do that. One is called forward modeling and one is called inverse modeling. Okay. So some of you might have heard about this way. So in the forward model, we don't rely on observation. So observations and models are completely independent. Like I was showing the earlier process that I showed you, that was completely forward modeling. Like from first principles, from our understanding of physics and chemistry, we are deriving what the planet's atmosphere would be like. So I'm only relying on two measurements, which is the mass and the radius. Only those are the measurements we use mainly, and of course the stellar parameters. Huh? So GCMs are general circulation models. So the models that predict the weather and climate for you, they are called GCMs. So these are the from first principles. If you are developing your model and then using those model to compare with observations, they are called then it is called forward modeling. Okay. So in this, many constraints are involved, like conservation of energy, equilibrium chemistry. All this we have to include because then we are within the physics laws of physics and chemistry. We are within that. Okay. But then the second approach that is also used, it's called inverse modeling. In the inverse modeling, what has to be done is you have your observations. Now we don't impose any constraints. We just take our still need our models, but with all these constraints relaxed. So what do? Is we have the pressure, temperature, structure, we have the chemical abundances, which are free to vary. They can freely vary as they want in our model. And then we generate a spectrum using those freely varying parameters and try to fit the observation. So in this, now we have not imposed any physics and chemistry. They're free to vary as they want, and then we try to understand what's there in the planet's atmosphere. So these are the two approaches we take. Both the approaches have their own pros and cons. In this case, we are a bit restricted, but we are sure that we are doing a right thing, like we are getting that is expected, like we are within the domain of our understanding of physics and chemistry. But when we go in this area, it can go anywhere. The values could be like we wouldn't expect. But that also gives you a very good fit to the observation. This will definitely any day will give a better fit to observation than that one. So now it becomes difficult which one is right or wrong. That we'll see, like with more measurements, that becomes clearer and clearer which one is more right. But currently we employ both of these techniques in our research. Okay. So that is what the inverse models I was talking about is. So in inverse model, we also get an opportunity to do, like we also get in forward models, is like, I don't know, someone was talking about Bayesian sampling. So this is what we do here. We try these hundreds and thousands, millions of these simulations we can do, because now we are not imposing any physics and chemistry. So computationally it becomes simpler. So that's why we can do millions of those runs, and then statistically what is the composition, what is the pressure temperature profile it is able to constrain, that we can get. We can also get the errors on them, like what is the range. All these things we are able to get using this inverse models. Okay, any questions until here now? I know this has become a bit steep learning. I'll again come back to simpler stuff. Okay, so this might be, so one of the interesting system, this was a very famous system, the TRAPPIST-1 system, where we had like 7 planets which are very in the habitable zone. So people have been studying, trying to study the atmospheres of these planets as well. So that has been done using Hubble Space Telescope first, but we all got like flat lines, nothing much. Yeah, almost, yeah. So there, but so see the habitable zone concept, I'll talk about that later. It's not as simple as it seems. Habitable zone is not like fixed thing. It's quite a, because it ultimately depends on what your atmosphere is made up of. Your atmosphere's composition and the presence of clouds can change your habitable zone. So the point I want to say is like we have been studying hot Jupiters, we have getting nice constraints like this, okay. But when we started studying Earth-like atmospheres, like terrestrial, using transmission spectra, we did not get anything. All are flatline. We don't get anything because if you have some absorption, you will see that structure there. You don't see any of those. So this was using Hubble Space Telescope, okay. And just wanted to give an example. This is one of the actually recent study where we use an Indian facility, the HCT, the Himalayan Chandra Telescope. So here also, for the first time using an Indian facility, we were able to see like detect a planet's atmosphere and actually measure the Rayleigh scattering slope in that. So this was a very, very recent study that that was published last year. Just wanted to show that using Indian facilities also we have started to do that, but still comparing to the space-based facility, this is nowhere. Because there you get a very good observations from space-based facility. Okay, so until now I have been like talking about transmission spectroscopy. So I will just give you a primer for emission spectroscopy. I won't go into the details of it. Like in the transmission spectroscopy, what we are measuring is, you know, when the planet goes in front of the star, there is a dip in the brightness, and this dip in the brightness we measure in different wavelengths, and we get what gases are present. But in that we are only measuring the limb, the planet's atmosphere, because we are not getting any information from this side. We are not getting, because we are going to the planet's atmosphere. So that is called the primary eclipse. Now we have one more observation that we could do, which is called secondary eclipse. In that, what we do is just before the planet is going behind the star, we take a measurement. So we have the measurement of star plus planet, and once the star planet goes behind the star, we take the measurement. So we have stars measurement. So star plus planet minus star. What you have is the planet spectrum.
But
So
the light is going that side, so
that side
planet
means,
is also emitting something.
that is what we are measuring the planet's light actually in that case. So that is what secondary eclipse is. So in the secondary eclipse, we are able to get the emission spectrum of the planet. And this is valuable. As I was saying in the morning about direct imaging, this is similar to that. We are able to get directly the planet signal in the emission spectrum. But because it's the emission coming from the planet, the number of photons are very low. The signal is very low compared to what we get in the transmission spectrum. Okay, so this is one of the major, one of the main techniques also to constrain the different properties of the exoplanet atmosphere, the emission spectroscopy, or what we call it as the secondary eclipse. Okay, so using a secondary eclipse, if it is tidally locked, then you can also, this is one example of a terrestrial planet. If it is tidally locked, then because this part is like lit, it will have an ocean, and other part will not have an ocean. Like, so this is an artist impression, this is not real. But because of tidal locking, these are all the different possibilities that could happen in exoplanet atmosphere. Maybe we can't say, I mean, it's a very complicated system. It might be possible. Okay, so I just will give a brief overview of, like, in transmission we were doing this geometry. When we were doing transmission spectrum, the light was needed to travel through full atmosphere. Okay, a large path length of the atmosphere. But in the emission, it does not need to. It's coming from the planet directly. Okay, so this has large implications because in transmission, you have to traverse through such a large part of the atmosphere, you can't go much deeper in the atmosphere. But in emission, you can get measurements from the deeper parts of the atmosphere. And this is one of the major differences between transmission and emission spectroscopy also. So I know you're all tired, so I won't give you the quiz now. So basically the point I want to take home is that with transmission spectroscopy, you can measure part of the atmosphere that is quite high but very small. Using emission spectrum, you can measure much deeper part of the atmosphere. So you can constrain the pressure, temperature, structure much more accurately with the emission spectrum. And this is what actually all the satellites that are going around on Earth is measuring. They are all measuring the emission spectra of the Earth. So all the satellites that give you the weather prediction and everything, many of them measure this emission spectra. Like INSAT series of satellites, you know, ISRO launches, that measures this because that is what it gives us the clouds and rains and sea surface temperature. All this is measured using the emission spectra. So the same concept now we are applying for exoplanets. Like we have a telescope that is far away. Using a secondary eclipse technique, we are measuring the emission spectra, and from that we can get the pressure, temperature, structure, its composition using the emission spectra of the planet. Okay, so this is too detailed. I won't go into details now. But the takeaway home point is that with emission spectra, you can also get different features and constrain the pressure, temperature profile more accurately. Okay, and this is one of the discoveries actually that we did in 2017 using the emission spectrum. So this was published in Nature. There actually, for the first time, we were able to detect inversion in an exoplanet atmosphere. Like I showed you, in the Earth's atmosphere, we have an inversion layer. So this inversion layer is because of which gas in the stratosphere? Ozone layer, exactly. So now that plays a very, very important role in preserving life on Earth. Similarly, for exoplanets, can we detect an inversion? So in this case, this was an ultra-hot Jupiter exoplanet, and in that case, we were able to detect a stratospheric inversion in the exo, and that was using an emission spectrum. So that was a very interesting study. Okay, and this is what the emission spectrum of Earth, like when spherical bands look like. So in the Earth's emission spectrum, if you go, you can clearly see H2O, ozone, CO2, all these things. In Venus, you can see CO2. In Mars, also you can see CO2. The main thing that we see differently in Earth is the ozone, which is one of the important biosignatures that is found. Okay.
So any other biosignatures?
Hmm?
Any other biosignatures?
By others are there. I'll actually go through that. Huh? DMS. So that is, so this is where I will come into like where we are heading towards. So the DMS thing I'll talk about in a minute. So with Hubble Space Telescope, we were restricted until 1.7 micron. Now with James Webb Space Telescope, we have all the way we have access until 28 micron. So because of that, we can measure many more molecules that are present. Plus the mirror size is also very big. So your signal is very high. Your 6.5 meter, 2.4 meter. So this leads to very high signal to noise ratio observation and much larger wavelength coverage. So here, so that's what we were able to do 2 years ago. The first observations that came using JWST, we detected carbon dioxide for the first time in an exoplanet atmosphere. And this was possible only because of JWST, because 4.2 micron was not covered by Hubble Space Telescope. So using JWST, we were able to do that. And you can think the carbon dioxide is so important, like for all the planets in the solar system. So this was a very big discovery that the full team was able to do. And this was done using JWST. Similarly, we were able to detect so many different molecules in one of the exoplanets, sodium, water. With Hubble, we were restricted until here. With now more coverage, we got more different molecules that are present. Carbon dioxide, monoxide, and all this, water. And that is where DMS also, like people started talking about in different planets. So this is just this is the name of our model that we have developed. So we use this model for all these measurements that we had done. So this is in my research group we developed a planetary atmosphere model to interpret JWST observation, and this includes all the different. These are the students working in my group who contribute to this development. So all this include, our aim is to develop a planetary atmosphere simulator that we can use to model any planet and interpret the observations of any planet in our solar system or exoplanets. So we are like working towards it. Of course, it takes time. So we have interpreted many. We have recently interpreted Hubble and JWST observations. We are able to do that, and we showed that for the first time that we need both Hubble and JWST to get accurate constraints. Okay, and here I also wanted to point out like India is also planning one more mission. It is currently in the plans. It's called ExoWorld. Have you heard about any of you? So this is an exoplanet mission which ISRO is thinking, which would be used to characterize the atmospheres of exoplanets in like 5 to 10 years down the line. So we are all working in the team towards that to like, because currently we are relying on JWST and Hubble Space Telescope. So India is thinking of that mission where we can target very few planets and study them in details and characterize their atmospheres. One is of course life is one of the important like is there life in any other planet? That will be one of the important questions, and also to get diversity of these different exoplanets that are present. Okay. So in the near future, where we are heading towards, we started with like stars, hot Jupiter, warm Neptune, and slowly we are getting towards smaller and smaller planets. But as I have like entire talk, you will notice the characterizing smaller and smaller planets like super Earth and terrestrial is very challenging, because the atmospheric scale height is very low, so it becomes very difficult to characterize this exoplanet. But that is what we want to do ultimately in the future. So maybe you are the people who will figure out some years down the line like how we'll be able to do that. There are already plans for the missions 15 years down the line. There is a habitable worlds observatory that is being thought of, where we will get an opportunity to do super Earth and terrestrial. Maybe with ExoWorlds we will be able to do some of these. But the aim is to get to the smaller planets and characterize them accurately, so that we can detect any hints of biosignature will be very valuable when we do this kind of study. So that is where we are heading towards. We are heading towards smaller and smaller planets, but it is really challenging to do them. So many missions are planned. You can all think of new ideas that could be done, but that is where the field is heading towards. Okay. And there was this question about dimethyl sulfide. So these are the different, so currently one of the areas also people focus on is what could be considered as an unambiguous biosignature. So now oxygen is a good biosignature, but it can be also produced using non-biological sources by dissociation. Same is for methane. So dimethyl sulfide is one of the gases which until like this is the old this thing. Recently, it is said that it can be produced using non-biological sources. So that result that was published for K2-18b planet, you might have read about. So it's a very controversial, and I myself believe that currently it requires a lot of proof. Especially the detection of DMS itself is controversial.
That research paper uses a lot of instruments. It find it difficult to understand.
Yeah. So means I can understand that paper. The main thing is about the detection significance. It is not that robust, especially for DMS. So we cannot be sure that that is actually a signature of biosignature.
Although they have given terms of 5 sigma.
Yeah, but that 5 sigma detection itself is questionable. People we have now known. Okay, so I know you have been patient enough to be listening to. I have rushed the last part because it has been too much. Okay, so these are the main takeaway points which we have already discussed. Of course, I'll open like the next 10 minutes for any questions, any queries, anything you want to discuss. I'm happy to take those. Okay, so we have covered a lot of ground in this. This generally takes like 2 weeks of lectures. But I have covered it in because we have limited time. Okay, because each of this has lot of details in it, and the chemistry can take full lecture. I take a planetary atmospheres course at NISA, so each of them is one lecture for me. Okay, so yeah, some question, yes.
So if we consider a tidally locked planet, let's just say gas giant. So when we see the transition lines, we are seeing only from the lobes side of the planet, right? Like the end part of the planet. So the atmosphere structure on the like opposite side of what we are seeing, so that could be very different, right?
Yes, very true.
So how are we able to, is there any way to detect?
Get that information. So yes. So what happens is that without JWST we were not able to do it. suppose the planet is tidally locked. If we are doing the secondary eclipse measurement, then we get the information from this. This will be day side, correct? Because the planets, the sun's radiation is coming. This is it will emit in this. So this is the day side of the planet. So we got the information of the day side. Now, if you want to get the information of the night side, then you can get from this. But you cannot get using transmission spectrum. You are relying again on the emission, but the signal will be very weak. But with James Webb telescope, because of its large mirror size, we are able to do that. So it's the paper is currently, I am part of that. So this is the first paper where we will be looking at the night side. Then one more paper which is soon coming out where we are looking at the night side of this. But these observations are really challenging. So as you said, that we can get both sides. From here the day side and here the night side. Any other questions? Yeah, feel free to ask any questions you have. It might be trivial also, don't worry. Okay? Yeah, go ahead.
Like, usually biosignatures means carbon-based life, right?
Hmm.
So if we have to find like any other combination form of life, how well could we see that? Like, how well could we recognize it as a life form?
That's a difficult thing. So currently, even when we are looking for life on these different exoplanets, we are only focusing on biosignatures that we know on Earth, because we have only one reference, Earth. So if there is a completely different form of life there, we won't be able to tell. It will be very challenging. So people are working, some biologists are working on what are the different possibilities of life. They are working on it, so maybe that will be helpful. But as of now, we focus only on our understanding of the Earth. So our biosignatures are also defined on what we see on Earth. Like DMS is there, CH3Cl, oxygen, everything. All these biosignatures are based on what we know on Earth, are the biosignatures. Any other questions? We can discuss. Oh, this is a tea time, no? Do you have more class after this? No. Okay, so yeah, if you have further question, you can ask me. Today I'm leaving anyways, but of course I'm open to like emails also. So if you have any further questions to ask on this topic, yeah.
So when you talked about the exoplanet detection method, both astrometry and radial velocity method is kind of similar, whereas in radial velocity you see the shift in the spectrum, and
Huh.
here the shift in the planet, like the star itself, right?
Correct.
So like why is why do we like do astrometry? Like what is the advantage of one method over the other?
One because in astrometry you don't have to do spectroscopy, no. Yeah, so you don't need a spectrograph. So in a sense, like instrumentation wise, it becomes simpler. That is the thing. And other is in to do spectroscopy, your spectral lines should be there or it should not be contaminated. So in astrometry, you can avoid that. So that is why its advantages can come into. Okay. So how many of you understood? Like how much part of this you have understood?
80%.
80%. Okay, good. I am happy about it. I guess the detection part is easy to understand. Yeah. Here, what happens in atmosphere part, you have to combine all the information. So, how many of you are coming from physics background? Okay, most of you. Okay, so that is good. So the physics background, you'll understand some of it. The chemistry part you won't get. But see, in the today's world, all the research is multidisciplinary. It's not like you're from physics, you're from chemistry, everything has to be combined. Because nature does not care like what you know or not. Ultimately, we have to understand everything in the holistic way. And that is what in exoplanet field is also like. When we want to understand exoplanets and their atmosphere, constrain them, we have to combine all this information to interpret what's in them. Okay, and here I have not even covered the GCM part, which is like whole another thing. Like we have to include all the different aspects of the model and everything. Okay, so yeah, thank you very much for listening, and yeah, it was good. Okay, I'll be here until like more half an hour or so. So if you have any questions, you can come to me and discuss.